Hopefully you paused the video and took the derivatives of f, g, and h. If you haven't, I'm going to pause it right now. Or excuse me, you should pause it right now because I am going to take the derivative of f, g, and h. F is 8 times 2 to the x. Now, this is an exponential function times a constant of 8. So when I take the derivative, f prime of x, I'm going to have that constant of 8 multiplied times the derivative of 2 to the power x. Derivative of 2 to the power x is natural log of 2 multiplied times 2 to the x power. Now, this is 3 expressions multiplied times each other, the order of which, it doesn't matter. So if you went 8 times 2 to the x and then times the natural log of 2, you could do that. But I prefer it this way. Notice that I did not have to go through the whole change of base thing. Once I know that 2 to the x has a derivative which is natural log of 2 times 2 to the x, I don't have to convert bases to find the derivative anymore. Let's utilize that property to do the derivative of g. So g prime, this is an exponential function with base 1/2. So we're going to take base of 1/2 to the 4x, take the derivative of that, and then because its base is not e, I'm going to have to multiply times the natural log of the base. So natural log of the base multiplied times the derivative here. Now, because my exponent is 4x, I need to pull a 4 out front. And so it's natural log of 1/2 times 4 times 1/2 to the 4x. Remember that, once again, if you have u equals e to the ax, then u prime is equal to a e to the ax. And all we're saying is that if we change this e to a 1/2, then we better multiply times the natural log of 0.5 out front to make that all happen. So if e gets switched to a 1/2, then it looks like the same exact thing we did with e, except now we need to multiply out front times the natural log of 1/2. Hopefully that makes sense. Let's take log base 4 of x to the 6th. Well, if we had a natural log of x to the 6th, what I would do to take the derivative, take y. What I would have done to take the derivative is I would have taken a fraction at 1 over x to the 6th times 6x to the 6th to the 5th, and then simplified that if I wanted to. But now, because we have a log base 4, I have to throw in another multiplication. So take h prime of x. We're going to get a fraction with another fraction. The first fraction is going to be 1 over the natural log of 4 because we have base 4 there. And then the second fraction is going to be this one. 6x to the 5th divided by x to the 6th. So with natural log of x to the 6th, I put the normal function in the denominator and the derivative of the function in the numerator. Because I have a log base 4, I have to take that and then I have to multiply it times 1 over natural log of 4. Some people will multiply these out and combine them. Either way is fine with me. If you want to keep your answer like this, go ahead. If you want to be really fancy, you can multiply as much as you want and combine as much as you want till you can get one fraction. So the top would be 6x to the 5th. The bottom would be natural log of 4 multiplied times x to the 6th. And then if you're really fancy, you'd say, oh, x to the 5th and x to the 6th. Since everything is multiplied on top, everything is multiplied on bottom, we can cancel out like terms. And an x to the 5th can go away, and you'll just have one copy of x in the denominator. So if you want to simplify, this is as simplified as you can get it. 6 over natural log of 4 times x. So that's how we take derivatives of exponential functions and logarithm functions with different bases. When you take it from an exponential function, you have to multiply by an extra natural log of the base. When you take a derivative with the logarithm function, you have to divide by a natural log of the base. So these are our straightforward rules, and they all come from understanding the chain rule and the other rules we've done before.